Introduction to Electrodynamics by Griffiths Problem number 2.13. In this problem, we have to find E field at a distance S from infinite long straight wire that have uniform line charge density lambda. And we have also compare our results with equation number 2.9, that is equal to E is equal to 1 over 4 pi epsilon naught 2 lambda over z unit vector. This is a equation number 2.9. So consider we have infinite long straight wire that have uniform line charge density lambda. To calculate E field, we need to imagine a Gaussian symmetry, that is coaxial cylinder in this case. Coaxial meaning having same axis. Now consider length of this cylinder is equal to L and distance from central axis to boundary of this cylinder is named as S. And consider a uniform E field is pointing in this direction, that is S unit vector. So to calculate this E field, we use integral form of Gauss's law, that is equal to according to integral form of Gauss's law close integral E dot dA is equal to Q enclosed over epsilon naught. Here dA is a area vector, that is pointing normal to the surface. Here we have three area vector as from figure. The first area vector pointing in this direction called dA1. The second area vector are pointing in this direction called dA2. And the third area vector are directed in this direction called dA3. So our integral form of Gauss's law is equal to close integral E dot dA is equal to close integral E dot dA1. Here we cannot add 1 with E because E is uniform, plus close integral E dot dA2 plus close integral E dot dA3 is equal to Q enclosed over epsilon naught. As you see from figure, area vector A1 and area vector A2 are perpendicular to E field. So we can say that E field due to dA1 and dA2 will be 0. So dA1 will be 0 and dA2 will also be 0. We have only E field due to area vector dA3 or due to this curved surface only. So this expression are reduced to close integral E dot dA3 is equal to Q enclosed over epsilon naught. Here our first task is to calculate Q enclosed by this curved surface, that is equal to lambda is equal to charge per unit length, and from here Q is equal to lambda into L. We just put this equation into this equation. We have close integral E dot dA3 is equal to lambda L over epsilon naught. As you see from figure, area vector dA3 and E field are parallel to each other, so the angle between them is 0. So by taking dot product of this expression, we have closed integral E dA3 is equal to lambda L over epsilon naught. And here closed integral dA3 is the area enclosed by this Gaussian surface or curved surface, that is equal to A is equal to 2 pi SL. We put just this area into this equation and we have E into 2 pi SL is equal to lambda L over epsilon naught. And here both L will cancel with each other and we have E is equal to lambda over 2 pi S epsilon naught. And if we talk about vector form of this E field, then we have S unit vector here, and that is E field enclosed by this line charge distribution. And our final task is to compare this expression with equation number 2.9. If we compare these two equations, then we notice that in this equation we have 2 missing in numerator as well as 2 missing in denominator. So we just multiply by 2 and divide it by 2 by this equation and we get equation number 2.9. So E is equal to 2 lambda over 4 pi S epsilon naught into S unit vector. That is exactly equal to question number 2.9, but here we have Z unit vector and Z, but in this equation we have S and S unit vector.